All right. We're going to start the live stream soon. So if we can get situated, we'll start the presentations. And this is a mic that you can just put on, like right here.
All right. Thank you. Hi, my name is Dimitri. I'm one of the runners of this meetup. Some recognition for organizers. I just want to say thank you everybody for coming. Every meetup I organize, I feel like there's 5 people, and there's 10 people sign up, and there's 15, and I think, oh my God, we're going to show up, and there'll be like 4 people in the audience, and then like last minute, we just kind of see this surge in the registrations, and it's great. So the only thing we worry about is, did we get enough food? I think we did this time. Thank you, Amazon, for sponsoring the food. And if you're interested in presenting at future meetups, come talk to me. We actually have one we've already started planning for about 2 months from now. We're thinking the theme for it is going to be Valkey 9X features. But beyond that, we'll probably do another meetup in 2 months after that. That's our current cadence. Anyway, now let me talk. I'll turn it over to our presenter.
All right. Thank you, Dimitri, for organizing it, and Madeline. Thank you, folks, for coming today. We'll do quick intros, and I'm going to try something somewhat controversial. I'm going to try to violate every law of live demos and do it. So what that means is I'll actually try to do live benchmarking on Redis and on Valkey, and we'll see who comes out ahead. Because one of my biggest pet peeves is blogs about performance benchmarks that are not reproducible. So we're going to try to go a step further. And if you want to follow along, you could. This is also recorded. You can follow along afterwards. That way you know it's not engineered or anything like that. So we'll get into this with that kickoff. Quick intros to ourselves. My name is Khawaja. I started my career building cameras for the Mars rovers. I'm super impatient. That's why I like benchmarking. Hardware is not very fast to work on. Like, it takes a while to see the results of fruits of your labor. So I moved into writing software, and I moved my image processing pipeline for NASA to AWS back in 2008 timeframe. Again, impatience works there. I joined Amazon. I was there for almost a decade. I ran the DynamoDB team, worked very closely with the Elasticache folks there as well. A lot of the folks from then are still on the team. It's exciting to see that as well. And today I'm a co-founder at a startup that also does caching. It's called Momento. I'm co-presenting today with Brian.
Hey, yeah, I'm Brian. I think my journey in all this stuff sort of started, I joined Twitter in 2014 and started working with one of my other co-founders, Yao, all the way back then. Obviously, things at Twitter eventually did change. So my team, which was responsible for doing a bunch of performance testing for the platform organization, we left and founded our own company. So we're basically doing the similar things to what we were doing at Twitter, but offering that sort of as a service and kind of taking our experience in benchmarking and caching and all that sort of stuff and observability and kind of spun that out into our own thing. So that's what I'm doing now.
Awesome. We work very closely together, the two companies. Sometimes it's hard to tell us apart, but we do different things. So just real quick about what Momento is, and then I'll get into the Valkey benchmark. It's basically a 2-tier cache, classic 2-tier system. We've got a routing layer, we've got a storage layer, we've got a control plane. And the routing layer authenticates, and it sends data to the request to the storage node, sends it back. Very straightforward. Can get into debates about why that's better or worse, but that's not what we're here to talk about. Today, we're here to talk about Valkey. But and benchmarking Valkey, and about that, there's a tool that we're going to use to gain some insights on what parameters to tweak. And that is the tool that Brian works on.
Yeah, so at Twitter, we kind of had a need for some higher resolution observability sort of stuff. I was working on the cache team there. And so we cared about, latencies that were sub-millisecond. Obviously, probably a lot of you are familiar with the demands of high performance stuff, so a Valkey meetup. But yeah, I mean, there were definitely cases where, minutely level metrics, or even if you had secondly level metrics, you might not be able to see everything that you want to be able to see. So I started working on this thing called Resolus, and sort of morphed over time, and now leverages eBPF very heavily, so we can instrument things in kernel space and really get a good idea of what's going on the system level. And this is really important for being able to understand what we see when we're benchmarking things. So there's a little dashboard view of some of the stuff where we ramp the load up on a Redis-like thing.
Called Valkey.
Called Valkey. I couldn't remember exactly what this one was from, but yes. So yeah, we use this in our testing and to be able to understand the benchmark results that we're going to show you.
Oh. One of the things that Brian omitted in his introduction, so Brian and Yao, they work together. They also, I guess they were bored, but they went and rewrote a memcache compatible cache in Rust, and it works really, really well too. But, they're hardcore engineers. We have performance benchmarks on that too, but that's not what we're here to talk about. So the plan today, we're going to talk about SLOs and metrics, dive into our target, lay out the setup, and walk through our plan to hopefully get there. We're going to do a little bit of primer along the way, intertwined with this, to cover the concepts we will use to drive the system hotter and hotter. We're going to do some tuning. We'll do it live, inspired by Bill O'Reilly. And we'll learn a little bit about what parameters to tune, how do we know what parameters to tune, and you'll see incremental progress as we tune those parameters. So the goal today is, we don't want to use a metal box and show that it could do 1,000,000 RPS. That would be way too easy. We're going to limit ourselves to 8 vCPUs. So this is a Graviton 4 CAG 2XL. That's what's going to run the server. And it doesn't matter if you can run 1,000,000 RPS if it takes seconds to get the results. So we put latency SLOs. We're going to try to get we're going to stick under 500 micros, half a millisecond, on the P99, and try to get under a quarter of a millisecond for your average latency. I usually don't talk about averages, but the Valkey benchmark tool makes a really big emphasis on the average, so we should talk about averages. It's also important for knowing the number of connections and so forth. If you could be bound on throughput by connections too if your average latency is too high. But we'll talk about both of those, and that's our SLO. We're going to try to make it real world-ish. Quick background on that. A lot of the benchmarks are very specifically tuned to the level of the packet size. Like I remember a blog where they were sizing the number of items in a pipeline to fit in a jumbo frame to demonstrate how you get to millions of RPS. None of that's going to happen here. We're going to try to be more real world, but the disclaimer is it's still a synthetic benchmark, right? So you want your benchmarks to emulate your specific scenarios, but remember that there's no better benchmark than production. We're going to try as hard as we can to make it real worldly. We're going to put client and server in the same availability zone just to minimize that variability. And we're going to go a step further, and we're going to put them in the same cluster placement group. Now, cluster placement group is, for some reason, not as popular as I would have imagined it to be. But it essentially allows 2 EC2 hosts to be co-located closer to each other. They're not going to be in the same rack necessarily. They are just going to be closer to each other on the network. And that just means there's fewer hops, there's fewer variability, on the network side, fewer packet losses, and so forth. And it just makes it easier for us to do more reproducible stuff. We're going to use the same node for Valkey and Redis. We're going to run one of them at a time, but it's the same node. So there isn't any like sleight of hand kind of, Valkey is running on a faster node than Redis or anything like that. You're going to watch me turn off Valkey, turn on Redis, turn off Redis, turn on Valkey. We're going to do all of that. It is going to use Docker, but no fake pipelining. So when we say a million QPS, it's a million unary requests. And we're going to do hundreds of connections, stick with 1 kilobyte item sizes, and 3 million keys in the key space. Brian reads the manual, so he knows that when you go to EC2 and you see a spec on the EC2 pages for how much bandwidth is available, remember, that's not the baseline bandwidth that's available to you. That's just the burst bandwidth. So technically, my benchmarks will violate the baseline bandwidth that's available to the host. But we're going to be running these benchmarks short enough so that the bandwidth is not going to get choked. But in his version of the test, he runs it with 128 byte objects so that you're staying under the baseline bandwidth. So that's one quick delta between the two things that we're going to do.
So test. Yeah, so in my test, I'm running closer to only about 1 gigabit per second effective, whereas Roger's tests are running closer to 8 gigabit per second, which is a little bit over that 3.75 gigabit that you're promised with a CHG2XL, but it's fine.
You're not really promised them, but that's the baseline bandwidth. Sorry, I used to work at Amazon. There's PR training here. Words like guarantees are rarely used. But that's what makes engineering more exciting. Now, we all have learned that context switching is expensive. And a quick exercise, like you all already know this, but I want to make sure that you remember this when you leave. We're going to do this as a team. The first 10 letters of the alphabets, A through J. Okay, so you don't have to count. J is the 10th letter. I'm going to count to 3, and I want everybody to just say A, B, C, D, E, F, G, H, I, J. Okay? 1, 2, 3.
A, B, C, D, E, F, G, H, I, J.
That was pretty fast. Now say 1 through 10 really quickly as soon as I say 3. 1, 2, 3.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
All right, awesome. Now I'm going to make it a little bit harder. I want you to say A, then 1, B, then 2, C, then 3. All right? Just a little bit more challenging. It should take you the sum of the time that it took you to say A through J and 1 through 10, right? All right, 1, 2, 3.
A1, B2.
You get the point. Luckily, we are. I'm not going to make a pneumocore analogy for human brains. That's all right. So now for the fun part. We're going to unbox the some EC2 instances, and we're going to run the baseline performance and see what happens. And hopefully, it will give the results that we want, which is it should be able to get to 1 million QPS, but we'll see. Oh, are you out of batteries?
Yeah, I think that's what's going on.
I have engineers for my team here, so I just want to admit one of the other rules I'm going to violate is I'm going to do some stuff on the console. It's on my dev account. They took my prod access away, so it's fine. All right. So what we have here, there's a bunch of instances running, but the two to pay attention to are is the CAG4XL instance. This particular instance is running in the same AZ as the other instances, and it has it's running in the same placement group as well. So it's running in a placement group called test.
Nice name.
And so is our benchmark instance, or the actual server instance. So what I'm going to do is, oh, can't give this away.
Sorry to interrupt. I just got a request from somebody. Is it possible to share the monitor directly or somehow zoom in because it's not clear?
I will try to make my fonts a lot bigger. If you're trying to read the full EC2 console, good luck. But I'll try my best to make the fonts a little bit bigger. Alternatively, I can try to, let's see. All right, I'm going to try my best. I'm going to reboot this machine so we can start fresh. All the configs will be lost. The only thing that will still be here is Valkey and Redis are installed on these boxes. But all of the network settings, all the pinning, all of that is going to disappear.
Make the text larger on that one too.
I'm going to do everything as root, violating all the rules. All right. So let's start with Valkey. And let's just see what happens out of the box. So Valkey is up and running. All right. You can see, maybe you can see, but it says 172.31.1493, 172.31.1493. We're going to run some 50 million odd requests, and we're going to use 384 connections, key space of 3 million, 11 threads on the Valkey benchmark. And the interesting thing here, and I learned this the hard way, was we kept tuning the I/O threads, and Valkey wasn't showing performance delta, but RPC perf was, and then it hit me. You got to turn multi-threading on the client as well. So remember to do that, and the same parameters work. But we're not going to mess with the Valkey the benchmark, but let's go ahead and run this benchmark. And we are at a whopping, what would you say? That's like almost 250,000 RPS, 236K. The problem is it's going to take forever because I told it to do 50 million. But you know, this is single-threaded, 233K roughly. The average latency is 1.6 millisecond.
And this is a pure write workload.
Pure write workload. Let me, yeah. So where it says -t threads. So now we're at 200 and we're at 285 KQPS. That's it.
Sorry, but the audio is not available on live stream. I'm like not tweaking, but slacking the text updates.
All right, Evan, is that like, are you feeding the audio? Okay. Is it back on now? We'll jump straight to the good part and just do 2 threads on Redis as well. Very close. So we were at 283, Redis is at 276. Average and P99 latencies are still pretty terrible here on both sides. They're equally terrible in comparison to what we will get to. I made a little scoreboard so we can keep score. All right, I'll take some notes. So all right. Average. For people who work on Valkey every day, do you ever love how autocorrect in Google always corrects Valkey to Valley?
You need to add it to your dictionary.
Yeah, but Google will still correct it to Valley. I don't know how to fix that. Okay, so 269K and 1.4 is the average. All right. So about the same. And P99, let's just not worry about this. This is just way too bad. Let's see what happens if we add some more threads. I'm going to jump straight to 6 threads. Any predictions? Well done. So going from 1 to 2 didn't really make a difference, or as big of a difference, for this specific workload. But going to 6 got us to 868K. Curious, well, I might want to trade with you and upgrade the batteries. All right, so with 6 threads.
Don't forget, how many cores do you have on the machine?
8.
The server, the Valkey, is running on an 8-core machine. The benchmark client is running on a 16-core machine.
And all the cores available to Docker.
That's right. All right, so just want to make sure I take accurate notes. Well, the latencies improved quite a lot too with this, with more threads. So average went down to 0.387. Oh, sorry. Should be 868K for V. And average was 0.387. And if we pause here, this is pretty fun to reflect on. Our throughput, more than tripled, and our latencies went down by a factor of 3. So that's pretty cool. Nice work, the Valkey team for I/O threads. I'm going to turn the same configuration on in Redis and just see what happens. All right, Redis improves a lot as well. You go to a whopping 618, 15, 14, 12, 11, 9, 8, 7, 6. OK, we'll let it finish. 596 KQPS. Not bad. I don't need to add a K here. All right, the average was 0.619.
Yep.
OK, and P99 is 1 millisecond. Let's just say 1.1 for Redis. And for Valkey, let's just scroll up real quick. Valkey was slower. 1.3.
It's a little unfair to compare latencies when the throughputs are so different there, though.
Yeah. 596 versus 868. Yeah, good point. All right. So now we have played with I/O threads, and this part so far is not quite rocket science. From like the Valkey team and the Redis teams have made it really easy to just turn that configuration on, turn on I/O threads, and boom, your throughput triples, latencies drop by a third. But let's actually get fancy. We're still pretty far away from getting to 1 million. So what are we going to do, Brian?
So, there's a lot of hiss on this microphone. So what we're going to do is we're going to look at why and what was actually going on the system level. So this is the Restless viewer looking at total CPU utilization on the server side in my test, which again was with 128 byte objects instead of 1 KB. But it gives us a good picture about how the CPUs are being used on this host. And we can see here with Valkey running that we have, we're at about 93% CPU utilization on the host, which is pretty good. One of our cores is running a little hot at like 97.7. So let's look a little bit further and see what is going on there. But quick, let's detour over to the client and make sure that the client is not where our bottleneck is. It's always good to double check these things. I was also using a much larger client in my test. I like to use a lot of resources when I do my benchmarking, but some of us are more conservative.
I practice frugality.
But in this case, the client is totally not the issue. We have so much CPU, we're only using like 30, 40% of the CPU on box. Like, we have plenty. Next slide. Jumping back over to the server side, we can look at the amount of time spent in user space. And this is where things get kind of interesting because we can see that, we're spending about 30% of our time in user space, But there's one core that's spending like 70% of its time in user space. So this kind of starts to expose what the threading model in Valkey looks like. We have one of those IO threads is actually like handling a bunch of the storage stuff. And it's spending basically all its time in user mode. And the rest are doing systems mode stuff like handling network requests and writing responses back out to socket buffers and stuff like that. But kind of sucks that like it's only using about 70% of a core. Like this looks like our bottleneck so far. Next. Let's look at the amount of time spent handling soft IRQ stuff. So when packets are coming in, we have our kind of hardware interrupts on the NIC where things are sort of getting interrupted and context switching to handle those incoming packets. But there's also the soft IRQ side where the kernel is handling the packet processing as well. So if we look at the amount of time spent in soft IRQ, it's like 27%, something like that. And it's pretty even on all our cores. Now we saw that our one core was at about 97%. User space time on that core was about 70%, so this 27% gets us there. Like we're kind of saturating when we combine our soft IRQ and our user space time on that core. Be really nice if we could get this out of the way and get that core up to 100% in user space, wouldn't it?
So because we're masochists, we decided to not use pipelining, because the idea here was to be, to show real-world tests instead of just engineer the benchmark. But what that means is there's a million packets. Like if you try to get to an RPS, you're sending a million packets. It's a lot of packets for the kernel to handle. And
that's in each direction. That's 1 million for your requests and 1 million for your responses.
Great point. And these soft interrupts are going to happen as soon as the packet arrives, and they're going to interrupt whatever core was listening for it. And if your Valkey storage thread is running on it, well, tough. Pinning allows us to isolate the interrupts to just 2 cores. Brian, I, and Dan in the Elasticache team have been debating about whether 2 is enough or not.
Right. So, I mean, we saw 27% being used for soft IRQ time. It's an 8-core box, so that's sort of really annoying because you need like 2 1/4 cores to really handle it.
2.16.
Yeah. I mean, so maybe it needs 2, maybe it needs 3. I don't know. Like, it's hard to tell.
But roughly 2 is what you need.
Yeah, let's start there.
So yeah, let's try there and see if we can get this up to 1 million. So this is very simple. Like core pinning, it sounds really fancy, sounds really crazy, but it's just a few lines on Unix. So the first thing we're going to do, we're going to type IP link show to see what the network interfaces we have. All right. This ENS34 is the actual network device that is on which the data is coming in. And what I want to do is I want to find out what are the interrupts. And you'll notice that for some reason, I don't know why, but for some reason, Amazon Linux defaults to having as many IRQs as there are cores on the box. So there's 8 cores on this box, so it defaults to having 8 IRQs. So when packets arrive, they will kind of interrupt whatever the hell's running on it, even if it's your Valkey application thread. So what we're going to do is we're going to say, you know what, let's get 2. And the command there is etool-l, name of the device. You say combined, and you say combined is just because the send and receive queues are the same. And you just say 2. So now there are only 2 queues on this device. Now what I'm going to do is, well, should we run this test again?
Yeah, let's run it again. We reduced it to 2, so I mean, there should be some resources for that main storage thread to run free.
Um, I'm going to do this with Valkey actually because it'll illustrate the point we're trying to make a little bit better because it runs a little bit hotter. So I'm going to run a caveman tool, which is htop. So you can kind of see what Brian was talking about. So now, what you'll see is Core 0 has almost none of the Redis or the Valkey stuff running. The Reds is mostly just kernel tasks. And but Core 1 still has some Valkey tasks that get booted when packets are coming. So we got to do one other thing. But let's take a look. We're still at like 8:15. Let's take a look at what we can do here. So this command, --CPU set, I'm going to tell it to pin the Valkey process on cores 2, 3, 4, 5, 6, 7. That's 6 cores.
No, I'm going to let you do that, but you realize what the issue is, right?
5? 5 threads? Oh, Docker PS? Kill the old, no?
You haven't moved the network interrupts anywhere.
Oh, I got to pin the network interrupts. Thank you. Thank you. Usually I'm not holding a mic when I'm doing this.
Yeah, so the issue that we're talking about is the fact that the network interrupts, if you saw where they were coming in proc interrupts, it was core 0 and core 7 because IRQ balance was probably running, so be sure you disable IRQ balance as well. Otherwise that's going to mess with us as we try and do really fun things. IRQ balance is going to try and be clever and mess up all our results. So we stopped that.
You want to explain what IRQ balance is real quick while I...
Yeah, so IRQ balance is a daemon that is running, and basically it tries to like look at the interrupt load and look at locality of the interrupt. So if you're on like an actual physical box with like 2 NUMA nodes, so you have 2 processors, or you have an AMD thing where it's all complicated, the network interface can be closer to some cores than it is to the others, and it gets really complicated. IRQ balance tries to do the right thing and tries to map the interrupts to the cores that are going to service it quicker, and it tries to look at all the devices with interrupts and try and spread things out so none of the cores are running too hot with interrupts, but we know better than IRQ balance does in this case.
In general, the operating system is trying to load balance and schedule things for you. We can just override that setting and say, please stay in your own lane for the IRQs, which is core 0 and core 1. So the way you do this is you, so we stopped IRQ balance. And then if you do the grep on the proc interrupts for ENS34, you see that there's only 95 and 96 are the interrupts, so the IRQ. So I'm just going to say, put a 1, which is pin this particular IRQ to core 1, and then I'm going to say,
No, you gotta index by 0.
4.
So
you know what? I'm going to just do. No, this is fine. This is 2. So this I'm doing SMP affinity, not affinity list. So this is 1, 0, 0.
No, it's still 0. Still 0.
No, 2 is 1, 0.
Oh, you're
So
doing yes. Okay. Correct. There are
Sorry,
two different
this-
ways to do this. This is using a CPU mask, which is a really masochistic way of doing this. I don't know why you're still doing this. But
It's basically 2 masks to 0, 0, 0, 0, 1, 0, which means that the second core, if you're starting from the end, is turned on. All the other cores are turned off.
Should be 96, but it'd be 96, right?
Thank you. This is called pair programming. All right, actually, I'll just show people how to do it the right way, if you don't want to be a masochist. If you say 0,
right, and put it out to the S&P affinity list instead. Yay, now we don't have to think in binary. Did you do that?
I did it again.
Yeah. Okay, now
All
it's
right.
good.
So the things to pay attention to is 95 is pinned to core 0, and 96 is pinned to core 1.
Thank
All
you.
right. Now we're going to run Docker with Valkey, and we're going to run Valkey on cores 2 through 7. This is 0 index, so it's the last 6 cores.
Your IO threads is 5 in that example. I was messing with him earlier and telling him to run this benchmark in some different ways, but there we go.
This is like code reviews on your benchmarks. I also recognize that I'm doing the Neanderthal version of benchmarking, where I'm manually testing things. But here, now you can see a much more interesting pattern.
Hey, nice. That core 6 is in like 100% of its time in user space. That's really good.
And the other thing to notice is the core 0 and 1, that's where the RIQs are pinned. They are saturated almost.
Yeah.
Let's see what the numbers look like. 1.02. So we beat the million by simply pinning to 2 IRQs. But I think we can do more. I'm going to try to just point out one other thing. Your benchmark node also needs to do IRQ pinning so that it's running efficiently as well.
Yeah, as long as you're using a smaller node, this is going to matter more, because you're going to have 8 interrupts on the next size up as well. So reducing that to get that out of the way, the benchmark tool helps. The other thing to note is that the P29 latency came down like quite a bit with that change. So that's always nice.
Yeah, P99 latencies are at 0.55, and the average went down to 0.293. All right, on the benchmark node, for reasons that I don't want to get too far into, Valkey bench is a little less optimized for this than Valkey itself is. I have other things to say about Valkey bench too, but we're going to put three queues here and give it a little bit more horsepower as well. So the 3 queues are all right, so I've pinned Valkey bench network queuing to the first 3 cores in the system, and I'll run it one more time. You'll notice Valkey bench has 11 threads, and I need to do a CPU set on this as well. Let's pin the benchmark too. So CPU set 4 through 15, give it 11 threads, 384 connections, everything else is the same. Right, got a little bit better. 1.05. Now you're really pushing these.
Yeah, those 2 threads handling all the entire queue are pretty hot at 99%.
Yeah, it's almost if they can use another 0.16 cores.
Yeah, maybe it does. Maybe 3 is a better number.
Yeah, we'll give that a shot actually before we end. There's another thing I'm going to do, as promised. Let's just see. This is a pretty, this configuration broke the 1 million QPS. Let's just run Redis with the exact same configuration and see what happens. Oh, we didn't meet our SLO. So the average was 0.343, and the P99 is 551 micros. So threads and 3 IRQs gets us to like 1.1 million RPS. So you can try that at home if you'd like. With a bigger load generator, because Brian has more funding than I do, he was able to get, what was the number you got on an 8XL?
I was getting like 1.24, 1.25 million QPS.
In all fairness, though, it was with a bigger load generator and smaller objects.
And smaller objects. Because I don't want to get bandwidth throttled.
That's right. So I think, did we cover all this?
No, this was sort of the, this is the sort of after view. So this is, again, looking with Restless at what was sort of going on. So we have total CPU utilization here. We can see that we have one core that's running kind of hot, but we've got all our soft IRQs out of the way, which we sort of saw with the HTOP stuff. And yeah, so now we see that the one core that is spending all its time in user mode executing actual storage stuff is at like 99.6%. So really good, like we're just kind of limited by the speed of that core at that point, or any other, if there are other optimizations. But yeah, this is great. All our soft RQs are concentrated on, in my case, this is with 3 network queues, so it's all concentrated on the first 3, and they're at about 78%, so we know that we're not saturated there. And here's where we see kind of one of the cool things. This is TCP packet latency. This is measured with an eBPF probe that measures from the time that the kernel says, hey, there's data ready on this socket to the time the actual application reads it. So this is purely the delay for Valkey to read from that socket after it got a notification through something like ePOL. And we can see that when we reduce the number of network queues and we do all this IRQ avoidance stuff, our latencies go way down for TCP packet latency. So this is where a lot of the gain is coming in. Our P29 went from 400 micros to 300 micros, and we kind of eliminated about a millisecond off the P39 and 10 milliseconds off the P49. So this really makes a huge difference, and this is something that you're able to see with Resolus because it's actually instrumenting and measuring that latency.
syscalls.
Yeah, so one of the other things that Resolus measures is the count of syscalls as well as syscall latencies. There's a bunch of stuff that you're able to get, again, using eBPF. So this is on the client side, and this is just sort of one of those things that makes me go, what? Because we're doing about 1 million QPS, but on the Valkey benchmark side, it's doing over 6 million syscalls per second. And if we go to the next slide, we can see that they're all in ePOL and friends. So one of the things, this is over 5 ePOL CTLs per request on average, which is not great. Like theoretically, you should just be able to do, ideally not many, you're just polling. If you go to the next slide. So the reason why this is because the benchmark tool is written using level-triggered ePOL notifications, and the whole benchmark is driven through these notifications. So level-triggered means that if the socket is writable, you'll keep getting notifications that the socket's writable. Not really super interesting when you're almost always writable, and generally you are. But the way the benchmark's written is that it needs these sort of notifications to kick off writing a request out. And then it re-registers as, hey, I want to know when this is readable. So it gets a response in, reads that, and keeps flipping it back and forth a bunch. So basically, just due to the way the benchmark tool is architected, you're getting these 5 system calls per request that you really just can't avoid. If the tool was written a little bit differently, like using edge-triggered notifications, you could probably avoid this. So that would be definitely an area to optimize the benchmarking tool.
And then maybe I can get the same results for the 2XL.
Oh, and then one other thing that I saw with system calls, and I didn't get a chance to look into this, is that there's some mutex contention on the client side when we're doing, so this is, our writes are happening first to warm up the Valkey instance, and then reads are happening at the end. But getting about 300,000 contended mutexes per second on the read workload is not great when you're doing about 1 million QPS, or 1.2 million QPS.
So quick summary, when you're trying to run the system as hot as possible, 5 to 6 I/O threads work really well. Turn down your IRQs to 2 or 3, depending on whether you're running 5 threads or 6 threads. Turn off IRQ balance. Pin the IRQs to some cores. Pin the Valkey processes to the other cores. Luckily, gravitons only have one NUMA core, so like you don't have to worry about NUMA locality or anything like that. And then do the same thing on the client side, and you'll get 1 million QPS. If you would like to not run your machines as hot, and you would rather have 750K, you can just run Redis. If you struggle to follow along because we were trying to, do this live and all that, a lot of the instructions are on the blog that sparked all this. We'll share that in the Valkey Slack. If you're not already on the Valkey Slack, please join. There's lots of help, lots of community. People are just helping each other out. No question is too silly. Ask away. I have been asking a bunch, and there's helpful folks who will just DM you and tell you what you're doing wrong. And that's been a really nice part of me, like the part that I've really enjoyed sitting on that Slack channel as well. And with that, I will pass it on to Q for the next talk, and then we'll take questions afterwards. Thank you.
Thanks.
You can give your lapel to
This is
Yeah, lapel.
This is for the video recording?
okay.
Yeah, so flip it onto your
So you
collar.
can just put it right
Yeah,
here.
yeah,
I'll try to get your
Like
screen.
this one?
yeah. Yeah, so put it the other way. So you'll put it like this. Front.
Okay, thanks.
I think so.
I think you can just
So this
say-
is the entire screen?
Yeah.
It's not mirroring? Okay.
And then use this for the people here. This is for the people on the screen, or the recordings later.
Okay. Thank you. All right. So this is another one of those rather unconventional talks I put together. This topic is memcache, which is a little strange. I guess given that everybody here knows about Valkey, Redis, everything, no strangers to those softwares, there is this other thing that's out there that still lots of people are using it. And there are very frequent questions when, before building a caching application, people are thinking, should I be using memcache or should I be using others like the kind of the de facto software nowadays, which is Valkey, Redis, right? So today, hopefully I will try to demystify some of these points. And yeah, so my name is Q Chen, and I am a senior software engineer at AWS in-memory services. We have Elasticache, we have MemoryDB, we have Memcache and Redis both offered in Elasticache. And also, besides that, I think in terms of the community, I am in frequent contact with the Memcache maintainer, which is nowadays just one person, pretty much one person running the show, Dormando. And I have a few commits which are in the open source Memcache and also in the client libraries for some of the Memcache drivers. So yeah, with that, I will start. So this is a bit of a brief introduction to Memcache. It was a general purpose in-memory caching system that's typically used to speed up web access to databases. And you see it very often times in mobile apps, web apps, gaming, advertising, e-commerce, right? You name it. And well, it's very performant, and also it's very easy to use, which are kind of its main selling points. It provides a very simple set of APIs that allows you to read and write to a very large hash table of key value. So that, in that regard, it's similar to Redis, except the APIs are simpler. Supports multi-threading. Redis, Valkey, well, fundamentally is still single-threaded, so I'll go into that a bit more later on. And also similar to Redis and Valkey, when the is full, your inserts will cause the older data to be evicted from the cache based on LRU. This is evictions. And also advanced caching use cases. In Memcached version 1.6, there are meta commands which supports advanced caching use cases. I'll go into that a bit more as well later on in the presentation. And lastly, data tiering. So we, memcached have the ability to move least used items to external storage called flash. Well, typically flash, but it can also be any kind of a disk drive. So yeah. A bit of a context on, sorry, this one. Okay. So a bit of comparison between memcached and Redis Valkey is, first thing to mention is memcached did predate Redis. It was released in May 2003 for a blogging website called LiveJournal. The owner of that website is Brad. He actually is the main maintainer for the Go memcached client nowadays. Memcached was originally written in Perl, and then it was rewritten in C and open source. So that Redis, it was released in 2009, which was several years later in February. It was used in the author's startup. Well, Salvatore was the author. And the company that we know of nowadays, Redis Limited, wasn't really involved until several years later. So yes, timeline-wise, memcached did come before Redis. And yeah, simpler APIs. Memcached supports string and numeric integer, so very simple. Redis Valkey, you have so many different data types, string, hash, set, list, and modules, you name it, right? So decision process becomes more complex when you're thinking about building application in Valkey and Redis. I mean, you do have more flexibility, but it's more complex. And memcached is truly multi-threaded, meaning that the command processing in memcached is multi-threaded by nature. And Redis Valkey is single-threaded command processing. That's, I think, probably everyone already knows. And here, the interesting thing here is that I was able to fit all the memcached commands on 2 slides. And it's impossible to do that with Redis and Valkey commands. So that also kind of illustrates how simple memcached was. So in terms of actual commands, on the top, first of all, data retrieval commands. So get and getS, it's the same as, well, similar to Redis or Valkey, where you do retrieve the value of a key. You can specify 1 or more keys in the command. So if you specify more than 1, it's a multi-get operation. And the difference between get and s and the get is that the getS command also returns you the version number for each of the items. So in memcache, every item is versioned, and whenever you update the item, the version number is monotonically bumped by 1. So the version number is also something that's interesting that we'll get to that later on in the next slide with the cast commands. And the storage commands is, there are 5 of them only: set, add, replace, append, and prepend. So set is similar to a Redis set command. It's basically unconditionally setting a key to a new value. Add is the same as a set, except it only operates when it's a new key. So if a key is already in the server, it fails. Replace is the opposite. The key needs to be already in the server. So if it's not in the server, then this command will fail. Append and prepend is just, you are concatenating content with whatever that's already there in the key's value. Yeah, so those are the basic storage commands. Numeric command, just increment, decrement, very simple. Redis also has it. You specify the key name, you specify the delta value, you will increment it or decrement it, and then it will return you the new value of the key. If the key is not found, it tells you it's not found. Lastly, delete. So again, the same as Redis, you specify the key name, the key is deleted. So those are kind of the basic CRUD operations for memcache. And this is a bit slightly more advanced, still pretty simple. So casts, in other words, is also known as compare and swap or check and set. So memcached have the ability to do conditional update. Essentially, the update only happens when the value hasn't been changed since last time you fetched it. So it's usually used in conjunction with the getS command. So you first do the getS, it tells you the value of the key and also the current version of the item. And then after you do your computation, you determine the new value of the key. You want to say, hey, I want to update the value only if nobody else updated the value before me. So then you will be using the cast command. You pass in the previous version number of the key along with the new value, and the server will do a check to see, is the version number that you know, is it still the most recent? If yes, then it succeeds. If no, then it tells you nope. So yeah, pretty interesting. And this feature can be enabled or disabled. There's a config option that you can disable cast operations, and you will not be paying this additional 64-bit of the version number per item that saves you some memory. Touch is basically update expiration of an item without fetching it. So it's like similar to TTL command in Redis. And the get command is like fetch the item's value and also update expiration. So it writes and fetch the value. Flush is the same as a flush command in Redis or Valkey, deletes all the data. And stats is similar to info in Redis or Valkey. It basically shows the server statistics. Yeah. And aside from the basic commands, there are, in version 1.6, there are some more advanced meta commands. It's follow the same structure as the original storage or retrieval commands, but have some new flexibility or new features added. There's meta get, meta set, meta arithmetic, doing increment decrement, and the meta delete. I think those are the major ones. One interesting thing to note about meta command is this advanced caching use case. And then one of them that comes to my mind right away is this concept of thundering herd. So when you have a caching application, right, and assume that you have a hot key, and the key was not present in the cache to begin with, what happens is that the multiple clients can request the key at around the same time, and all of them will see the cache miss, right? And when this happens, so if you can imagine, right, the client 1, it tried to do a get on the key, it gets past cache miss. And what it will try to do is it will then try to go to the database and fetch the key and then put it into the cache. But if at around the same time, another client comes along and tries to fetch the same key, he will also get back a cache miss and, and he will also try to go to the database to fetch the value. So the problem here is that when this happens, the database is going to be swamped with requests that try to fetch the same value. So essentially, database is doing the same work over and over again. And this is something called the thundering herd, is that the database can be overloaded when a hot key is being fetched from multiple clients, and all of them are seeing cache miss. So how does the meta command help the situation is, the meta get command has a feature called vivify on miss. What it does is that when you try to do a lookup for a key, you can specify this option, this end option with a TTL specified, so that if a server realizes that this is a cache miss, it will create the item in the cache as part of the meta get command with an empty value, and it will tell the caller that, okay, you get a cache miss, but there is a W, right? The letter W is also returned, meaning that you won the lease on the item. So you can go and recache this item if you can. And this lease is being held for 10 seconds, as in this example. So here, this client will then try to go to database and fetch the key. That's fine. And if the next guy comes along and try to do a lookup on the same key, he will get back a miss, but also he will get back an indicator that, okay, you do not have the lease on the item. So that's indicated by the letter Z here, which means stale. So when that happens, this other guy at least have an indicator that, okay, somebody else is fetching the key from the database, right? So he doesn't need to go to the database. So this is a pretty interesting solution to the problem where this feature actually helps prevent the scenario when multiple clients overwhelm the database upon cache miss. And only one client can fetch the value from the source database within a certain time frame. So yeah, that's the interesting scenario. Okay, let me go. And then obviously, After that, the first client will get to put the value of the key into the database, into the server, and then everybody will start getting cache hits from that point onward, and everything's happy. So, okay, so next is I'm diving into some Memcache architecture. So first of all is multi-threaded, right? What it means is that when client connections are accepted into the server, they are accepted using a single acceptor thread. So you can think of it as a main thread. And once a connection is accepted, it gets dispatched to a background worker thread. And the worker thread can handle reading and parsing, reading additional bytes from the network, parsing the commands, processing the command, and replying with the responses. So that's all happening on the worker thread. And this part is different from Redis or Valkey because they're single-threaded in terms of command processing. There are obviously multi-IO worker thread that can handle the multi-IO layer, but in terms of the core command processing, is still single-threaded today. And the number of threads you use to process the requests can be customized. So there's a parameter called -t. You can basically use it to configure how many threads you want to run. Typically, people will try to look at how many CPU cores you have on the machine, and then based on that, they make a decision on this parameter. And also, one last interesting thing is that the multi-get operations. So multi-get operations, you can read values on separate threads. So one single command with multiple keys, trying to retrieve multiple keys, the keys can actually be fetched on multiple threads. So there's no guarantee for a single point in time snapshot of all the values. Because if you're trying to fetch one key from one thread, another key can be updated at the same time on a different client connection and fetched on a different thread. But in Redis or Valkey, the nice thing is that you have a single threaded command processing, so then all the keys, that point in time is where all the values will be fetched. So yeah, that's a bit of an interesting point to know. And here is a bit of memory modeling for Memcache. Memcache store memory in something called slabs. Slab is essentially something that's associated with a certain item size. And when you request a page of memory, well, a page is usually 1 megabyte of size. It's associated for a particular slab class. So if you're trying to store items with certain size, then that will determine the slab class that the item will fit in. And then once a page is allocated, it's then divided into chunks based on item chunk size. So here on the left, you can see that example is that I have two slab classes. One of them is for 256 KB chunks. The other one is for 512 KB chunks. Well, they usually work in increments of doubling the size each time. So 1 megabyte page can hold 4 items in slab 1, and it can only hold 2 items in slab 2. So I stored a bunch of 512 KB and also 256 KB chunks in both slabs. And one interesting thing to note here is that traditionally, when a page is assigned to a slab class, it's there. It's there forever. You cannot move it across a different slab class. So here, what happens on the right-hand side is that the problem is if those items expires. So if those items in this page expires and no longer are in the cache, and I try to store a new item in this slab class, and if I don't have memory, if I'm at max memory, for example, there's no way for Memcache to free up a page over there and then move it here so I can store the item here. So but instead, I need to make room by evicting from this slab. And basically, I need to get rid of the oldest items from this page to make room for the new item. So that actually is a big problem for a lot of our users because the inflexibility of slab rebalancing can lead to situations when you have evictions, even when you know you have memory that's available in the cache, right? So we have lots of customers asking about this. And the solution is obviously to enable the slab auto mover. It's a new feature that was made available in Memcache 1.4.25, which means you can free pages from one slab class and then reuse it in a different slab class when you need to store items in the other slab class. So yeah, so you basically need to enable this feature. And LRU is the next major important point for the memcached architecture. So in 1.4 and earlier, the LRU is implemented as a double linked list. So I have a double linked list here on this page. So new items, we always insert to the head of the list, and then evictions, we pop items from the tail. And if the item is accessed, then it's unlinked from this double linked list and then put into the head. So that's called bumping the item to the head. And there's no background thread to actively maintaining the data, so that if an item expires, then it stays in memory until you try to access it the next time. And then we will do a lookup. We see the item have expired, then we delete the item. We free the memory. It's similar to Redis passive expiration, right? But here the problem is that it limits flexibility for multi-threading, because if you have frequent access to multiple items at around the same time, then you have to be frequently bumping items out of the in this LRU linked list, and that can cause the mutex contention. So if you have multi-threading, and then all of the operation essentially will end up being sequentialized, and that kills multi-threading, or that kills your parallelization, right? And in fact, what happened is that scaling beyond 8 worker threads in this design is very difficult because of log contention on this linked list. So what happened is that memcached came up with optimized LRU. That means the LRU, rather than a single linked list, it's segmented into multiple parts. It's called, there's a hot, warm, cold, and temp. Temp is actually not activated right now by default. So what's being used here now is mostly hot, warm, and cold. So like obviously the items which are newly created items, they go into hot, and the items at the tail end of the LRU within each category will get moved down to the next lower tier. So there is a thread, there's an LRU maintainer thread that's responsible for managing the item's lifecycle, so that it iterates over each of the sub LRU. It peaks at the tail of each of the LRU items. And if the item has been accessed, then it gets bumped within the same tier. Otherwise, if the item hasn't been accessed, it will be moved down to the lower tier, which is the colder tier. And if we see an item which expires, that we will trigger the item to be deleted, which is, it's active expiration basically for Redis. Yeah, so this actually helps scale read-heavy workloads pretty well, because now you have multiple mutex happening on different segments of the LRU, and they're independent. They can be independently updated or looked up, so that they were able to scale the workload linearly up to 48 threads rather than less than 8 threads. So yeah, and obviously evictions. If you are out of memory, or if you are at max memory, then evictions, we always evict from the cold tier. So we don't go evict items from the hot pool. So basically the idea is that if the item is hot, it stays in a memory as much as possible. And yeah, so.
Does the heat get bumped back to the null list?
Yes, so if you have items here in the cold tier and you are accessing the item will become active again, right? And then it will get moved. It will be able to get moved back to the warm tier. So, yeah. And this is the item mutex locking. So, in order to do parallelization across multiple threads to do item read and write, we need mutex locks, right? And the mutex locks are happening on the hash table level. And so, one example is that if you have a hash table with 1 million buckets, there are around 32,000 item logs. So it's not a log per item. It rarely need that, right? So, and there are secondary logs per slab class, so that different size items have their own mutex. And within that, you have hot, warm, cold tier, so each of them have its own mutex logs. So that kind of helps you parallelize read and write across different segments of your key space. And if there are concurrent updates happening in the same bucket at the same time under the same lock somehow, and it probably doesn't happen very often, but if it happens, it will be first come, first serve, meaning it'll be FIFO, and everything is sequential and properly atomic. And one other thing to note is that we only need to acquire the lock when we try to examine the memory, or we try to examine the item's memory. So if you're trying to write data to the network, to the client, you don't have to hold a lock. Yeah, the Memcached is did certain trade-offs, right, to support the generic use cases. It doesn't have to get to the level per item level locking. Yep, and then data sharding. So Memcached shards data on the client side. It does not require data sharding on the server side like Redis or Valkey. So the client is free to decide on what strategy to shard the key based on. For example, some of the very popular hashing strategies like CRC, client is doing it, as opposed to server doing the CRC and then computing, deciding which slot the key falls in, and then sending redirects to the client if it doesn't belong there. And consistent hashing is another very popular library that a lot of the Memcached clients implement, right? So, and that way, the client does not have to handle server redirects. For example, the moved redirects, like in the Redis or Valkey. Memcached clients still have to have a way to discover cluster topology. Like it just need to know which nodes are there, but it does not need to know which slots are served by which node on the server. And then all the complexity around migrating slots in a reliable ways and making sure the keys are migrated from the source to target, and the slot ownership is properly handed off, like the stuff that's happening in Valkey community. There really is no need for all of that complex work because Memcached client is doing all the data sharding. Obviously, the cost is that when you reshard your cluster, or like for example, you add a new shard into it, you will have cache misses when that new node comes up, and then you do need to warm it up. But for cache, that is perfectly acceptable. Yep, okay, so the last thing about Memcached is ext store, or external store. It basically extends the memory space onto flash or a similar storage, and it tries to move values to flash. And the key and the item's metadata that includes the item structure and the flash location where the item is being stored will stay in the memory. Idea is that when you reach max memory, the items at the tail of the LRU starts to move to flash to free up memory. And that way, it tries to keep the most actively used data in memory for optimal performance. And it's very simple. It uses a thread pool for I/O. So it's again, that thread pool size is configurable through a parameter, ext threads. And you only have to go to flash if you are trying to read items that are stored on flash. If you are trying to override items value, it does not have to go to flash. It will overwrite the value of item in memory, and it will invalidate the location on flash where the previous value is being stored. So lots of optimizations here. And obviously, the stuff that's on flash over time, it starts to get fragmented, and it has ability to compact existing items on flash to reduce the fragmentation of the disk. And also, it tries to only spill larger values to flash, and the smaller values will stay in RAM. It actually recommends that if your value size is less than 60 bytes, you don't actually save much by spilling it to flash. Even if you spill it because of the overhead of storing the item on flash, it requires additional DRAM, right? So your item should be bigger than that to leverage SSD property. And another interesting thing about the ext store is that if you are in a situation of writing a lot of new data into memcache and you're writing at a rate that's faster than the items can be flashed to SSD or flash, the items are evicted from memory to make room for you to store the next item, rather than making you wait for the flash to be available and then spilling the items to free up memory. So this basically prevents performance issues like the client see higher latency because of flash drive is hanging momentarily or unreachable or it doesn't function properly. So that's essentially it will degrade. Even if the flash goes out, it will degrade back to the in-memory mode of you try to write something to memory, we evict to make room for you and so on and so forth. So yeah, it's basically prioritizing availability over other aspects. Yeah, so that's pretty much the end of the presentation. So that here's a bit some more info on memcache. You feel free to kind of read up about it in more details, and that's it. Yeah, thank you. Okay. I think do you have questions?
Yeah.
Yeah.
Is the flash meant to be more of an availability thing, or is it also meant for somewhat of a durable storage or tiering, something like that?
Tiering of the data is, so the flash is mainly there as a means to expand your storage, right? So if you have item sizes which are big, say KBs, several KBs or even megabytes, right? It makes sense because if you store that value on flash, you save a lot of memory. You're going to reclaim that DRAM, right? So that way you can store more items. And also flash is typically cheaper than DRAM, so then you can also reduce the cost of your item storage that way.
So this is not a contingency thing. It is meant for regular use, like all the time you can use this.
Depends on the use cases, right? Like because it does use LRU to try to keep the items, warm items in memory. So if you have, for example, you're accessing a subset of your items all the time, but most of the time, and then you have items which are cold, then it makes sense. But if you're very evenly hitting all the items in your key space, then probably this is not the solution for it. Yeah. Any other questions for memcache?
Does anybody have questions from a previous talk?
Oh yeah, questions for.
Yeah, Q, one thing you said about when you do you talk about slot migration and how you divide the key space in the server side, and there are some advantages to that. It's not just about doing this in the client side has advantages, but it also complicates a lot of the clients and has all of the burden of doing consistent hashing or some other partitioning of the data in the client. So there are trade-offs. I think we should. We can talk about it, but there are trade-offs. It's not like one.
Yeah, sure. It's there are obviously trade-offs, but then if you do on the server side, there's additional complexity, and also, obviously, I think the fact that you get cache misses whenever you reshard is a major con of doing it this way. So, yeah.
We do have operational experience both with memcached and Redis and Valkey, so we know their.
Yeah. Yes.
So what is for client-side sharding and does everybody write their own thing, or is there generally like a standard that is being used by a lot of users?
Typically, each of the clients in open source, like memcache obviously have different clients, right? But typically what happens is that in each of the languages, there's one major client. Maybe there's a few minor ones. So the clients are usually implementing their own hashing algorithms.
Okay.
So for example, in the Java client, they're using the native hashing. They have FNV hashing. They have like CRC hashing. They have Katama, which is kind of consistent hashing, right? So I think Katama is pretty common. Like even in the PHP client, they support Katama, because everybody likes consistent hashing, right? You have, whenever you add new server or you remove servers, the amount of shuffling of keys, is minimized. So that. But yeah, so each of the client is free to implement their own hashing algorithm. Yeah.
Katama by default uses MD5, but
Yeah, true.
Yeah, I was mostly talking about the consistent hashing. Yeah.
Mm-hmm. Yeah. Yeah, I mean, you know like the topology of the cluster, you know like which nodes are there, right? You place them into the consistent hash ring, and then, but that, yeah, all of that is on the client side. Yeah. Yes.
For the match cache, what is the specific? Because we often heard like people use the Redis or Valkey more.
Yeah.
What is the special like a sweet spot for the match cache for custom use?
Well,
Could you repeat the question for the comment?
so the question is, what is special about Memcache? Why? Like, what makes people decide to use Memcache versus Redis or Valkey? I think nowadays what happens is that Valkey and Redis has become the default, right? Like whenever people think about caching application, the first thing they think about is Redis and Valkey. I think that's correct mindset, because you do have a lot more tools in your toolbox if you decide to use Redis or Valkey. You have hash, you have all kind of data types. Also, I think performance-wise, Redis and Valkey is getting pretty close to Memcache. I have some performance numbers actually, but I don't want to show it. But yeah, it's getting pretty close with 1 million requests per second. Memcache is, it hasn't really been changed in the last too much, right? In the last decade. It works, it's pretty reliable. It's multi-threaded, so in some certain cases, it's more performant than Redis. But I think in vast majority of the cases, you will find that Valkey performance is more than what you need, right?
in high eviction cases, Memcache has much more stable tail latencies. If you use one of the high resolution telemetry to observe tail latency, and you have a fair amount of eviction happening, especially override type of eviction, then Redis's tail latency can be very unpredictable, even at fully load.
I think it's probably coming from the fact that Redis is single-threaded in terms of.
No, that's because Redis doesn't have its own memory allocator, and Memcache has a slab-based memory allocator.
Yeah, but with that, it also comes with additional complexities like evictions in the slab, right? I mean,
But you're not calling free and realloc and that sort of thing on your hop path, which has unbounded tail latency. So you don't see it in P99, you see it in P99.
yeah. Okay. Thank you.
Are there any questions about the previous presenter?
Okay.
I think we kind of rushed to the second presentation. So.
Yeah.
Can I?
Yes. So, are the features in the new Linux kernel's extensible scheduler? I think it's a BPF based. Are those helping? Do those help with those sweet RPS numbers we saw?
So hopefully those do start to be kind of useful as that gets stabilized and people start implementing stuff and it gets into production environments and stuff like that. But stuff, the extensible scheduler stuff using BPF to program it is all still fairly new. So I think there is some exciting potential there where maybe you won't have to do some of the same tricks. But I do still think that setting the number of network queues to a reasonable number, because at the very least you're going to have the hardware interrupts coming in, which can cause kind of cache locality sort of issues there, right? Like if you're bouncing those cache lines out, that can hurt.
I have a question. So, in the talk, you actually, that most of the IIQs are happening because of the network, right? Okay, I haven't kept up with the kernel in a while, so maybe this question is like a little bit naive, but at some point I saw something where people said, hey, like instead of giving an IRQ per every packet, if you're on a high load server, we don't even deliver IRQs. We are going to let the application just pull. I forget what that is. I don't know if it was a system call or whatever. I don't know why we don't have that. Maybe if that's completely wrong, please ignore it.
Yeah, so the yes, there are polling-based methods where you can avoid at least the hard interrupts. A lot of the time, though, that 27% was actually the soft IRQ. So unless you move the network stack out of kernel space and into user space, which is viable, I just haven't seen it really done in big production environments with these types of cache workloads. It's theoretically possible, but yeah, a lot of it's just the incoming packets still need to be processed by the kernel TCP stack.
So I noticed you use 384 connections in the benchmarking. Have you tried more connections or maybe less connections and see if that also impacts the latency, throughput, and also the number of equals? Have you tried that?
Yeah, so the equal rate on the client is going to kind of be dominated by the amount of RPS that you're pushing, since you have those 5 per request. There is some amortized cost with like the actual polling, where you're going to get a bunch of requests in at the same time. On the server side, that stuff is all amortized like very nicely. You're not paying a huge cost there. But yeah, I mean, performance is going to vary greatly as you increase or decrease the number of connections. I saw pretty flat results. I tested as low as like 128, and I tested up to 1024 while preparing for this talk. And the numbers from Valkey benchmark were pretty consistent across that range, within maybe about 5 to 10% sort of margin. Other tools, it might not push up much past 1024 connections. You might need to use multiple load generators, which is something that I do like to do when I'm doing larger scale performance testing. Is use, maybe 4 or 8 load generator clients, point them all at the same cache backend, and kind of measure the performance that way. It really eliminates contention in the load generator client as a cause for that latency. It's really tough to measure things properly. It's really tough, especially when you're testing like these really fast cache services, right? So you really want to be careful to make sure that that latency that you're measuring is actually coming from the server and not coming from the client. So that's where I have worked on my own benchmarking tool, and I'm sure a lot of other people in the space probably have as well.
We use that tool. It's called RPC Perf. Brian is the author on it. We run nightly jobs on it where we'll run this test. All of the metrics are plugged in. It goes to open telemetry, and then we can see small artifacts changing. And yeah, like being able to have a distributed test harness goes a long way in eliminating contention on the client side. There's another system, like Brian has some automation as well, where you can, with a couple of clicks, run the configuration across lots of nodes on his the robot army of RPC perf nodes as well. The other really nice thing, we didn't get into it too much, but Valkey bench, one of the problems is that it inflicts as much load as the server will allow it to. And that has problems with coordinated emission, where I think what you really want to do is target a particular TPS and keep pushing that TPS, because in production, things are not necessarily going to relate themselves, and you can get into throughput versus good put versus bad put issues, as Mark Brooker explains it in his blogs. RPC perf allows us to target a particular rate of traffic, and also create spikes, drop the spikes, create them again, interesting patterns, and then we take all of that data, we coalesce it across the nodes, and then we can see it in our regular operational dashboards, and that's been super useful.
Just curious, have you tried like 10K or 20K connection to the server?
You had 8K, I remember, because you had the 1K configuration on 8 nodes.
Yeah, I mean, with RPC perf, I've definitely pushed it that high. One of the things, Valkey benchmark's a little hard to get latency numbers from in a distributed test setup, right? Because you only have those percentiles, and you can't really combine those across like 8 nodes in any sort of meaningful way. Like averaging P2 nines or 3 nines is just kind of useless. Really what you want to have there is the full histogram distribution, so you can merge the histograms and then export percentiles from that. And again, like as Khawaja was just saying, like you want to compare those latencies at fixed load levels, and you want to have more capacity in the client so that you're not over measuring the points where the cache server is behaving good. That's basically the short version of what coordinated emission is the benchmark tool slows down and measures less when the cache server is being slower, right? When you fix the rate limit and you have sufficient number of connections so you're always being able to dispatch on time, then you're always kind of sampling at that rate. So you'll have those representative captures of the bad moments and the good moments and not oversample the good moments. So that's where the latency measurements can be a little tricky as well. Everything about benchmarking is hard.
I just try to speak loud. Were there any insights from Redis for the last test where you're comparing Redis and Valkey, and Redis could not actually keep up with the throughput?
So I need to look at that a little bit more. I didn't realize that we were going to be comparing Redis and Valkey at the end there. So I haven't had a chance to look at that, but I'm definitely curious to see kind of what's going on there and see if there's something in the that this list shows us.
Yeah, you can see the artifact of not prefetching on the Redis side.
Yeah, we might see it in, potentially like L3 cache hit rate or something like that. Like there might be some metric there that's going to show us from the performance counters.
Of course, have you run those tests on Memcache? All right, just want to say thank you everybody for coming, and thank you our sponsors, Memento and AWS for the food and space. We're targeting one year, like I said, in a couple months. The theme is Valkey 9. If anybody wants to host, I'm looking at you, Osama. We are looking for space. If not, we'll find somebody. But yeah, so maybe mid-August, that's the time frame. And if anybody also wants to do some presentations, we'll do that. And beyond that, hopefully another meetup in the fall. Thank you so much, everybody. Glad you came.
We also ordered way too pizza, so if you want to take a whole pizza home, please do it.
Thank you.
It's been a while.